Okay, happy return. So rates of change in trigonometric functions. In advanced functions, you are continuously, almost chapter by chapter, coming back to these rates of change, right? So either average rate of change or the instantaneous rate of change, which definitely are useful, and we certainly utilize these rates of change kind of all over sciences, from engineering, computer science, businesses. Okay, you kind of name it. And in advanced functions in grade 12, you keep kind of chugging along this topic of rates of change. So in this video, I again want to try to bring it back for you. So the regular rates of change for trigonometric functions, they do not change. So the definitions are the same, right, as you've always had them, okay, for both average and instantaneous rates of change. But of course, you're dealing now with trigonometric functions, so sines or cosines or tangents and cosecants and so on. So it is worthwhile to try to touch base on this topic. All right. Now, if we take the standard sine function, right, you by now in grade 12, you should be used to how it kind of looks like. So this is all in radians, right? So we know that we have one period, right? So if I go along in here, I can kind of go and sketch this along. Okay, so here's my one period of my sine function. It's pretty kind of straightforward to see that, you have a maximum and a minimum for all these sine functions and cosines. Not so much for tangents, okay, or cotangents, because they go off into infinities in both directions. But for sines and cosines, it's pretty nice, right? So we have a maximum and a minimum. Now, at these particular points, you may remember that if you wanted to know what the instantaneous rates of change is, we know that it's going to be basically just a flat tangent line, which has a slope of 0. And that happens in all your maxes and minimums, at least local maximum and minimums, that you will have for these sine and cosine functions. Okay, so that's one thing that I would want to point out as you're kind of studying this, is that we know, okay, exactly where these things happen. Because for a sine function, right, if you go back to the unit circle, right, you can kind of remember when sine of x is equal to its maximum or its minimum, right? So that happens at pi over 2, and then at 3 pi over 2, or at minus pi over 2, right? So those are the 2 points, and if you would be drawing your tangent line in here, okay, and if you were trying to do a flat line, well, it's pretty clear that it's going to happen at this point, and then it's also going to happen at this point, and then it keeps repeating because these sine functions, okay, are periodic. Now, the other thing that we should kind of notice is we should note when we have the maximum slope for these sine functions, right? So either positive slope or negative slope in this direction. And if you're just observing the graph itself, you can probably tell, if I kept drawing these tangent lines. So for instance, if I keep drawing it from that maximum point, and then I draw it, let's say right here, I try to attach it. Okay, so notice that, you went from 0 and then it goes negative, and it will stay negative for us. Okay, so just keep going and being negative in this way. Okay, and then I can attach it in here, and then eventually, it's going to get to its maximum slope, right? So maximum negative in this side, and then it's going to go back again, and it's going to try to level off. Okay, so in here, so it's going to try to level off, all right, as we get closer to here, and then eventually gets to that 0, and then it takes off again, right, in this direction. Now it becomes positive, right? And then it will do the same thing. So over here, it's going to level off. So why am I talking about this is because at the midpoint, okay, between your maximum, right, and then your minimum, okay, at the midpoint is actually your maximum negative slope. And then the same thing happens between your minimum and your maximum points. You will have your maximum positive slope happening, okay, at the midpoint there. So that's something that you should notice, that your instantaneous rates of change can be maximized at the half point between your max and your min, right? So you're basically 0 tangent lines that you have in there. So if I'm going to change the color right here, okay, and then I'll try to write it out for us, and then also highlight it maybe. So the maximum point is going to be happening basically right here. Now it also happens right here, because if we continued on that sine and went on, we would have gotten to a minimum. So here's my max, and then here is my min, and then halfway through, which basically is pi, right? Okay, and then 2 pi, right? So it goes 0, pi, 2 pi, 3 pi, and so on. So it alternates between a positive maximum, right, at 0, then it goes at pi because it goes on the negative direction, right? So it'll be your maximum slope of negative, okay, at that pi, and then it alternates. And you can do the same thing with the cosine functions, right? So if you would graph the cosine functions, you can take your peaks. You know that the tangent lines, the instantaneous rates of change there are 0 at those points. And then halfway in between, we can figure out where that is. Now, that's for your standard sine or your cosine. Sometimes you might be given, right? So in terms of, it might not be a pure, beautiful sine function, right? It might be sine which is transformed. So in those transformed functions, we can find the whole period, and then we can divide that period up so that we can find these maximums and minimums accordingly, and then the maximum and minimum slopes, okay, that we would want to have. Now, if you want to compute specific, let's say, average rates of change between 2 points, which basically is plotting 2 points up and drawing a secant through it, okay, so on that interval, you can figure out what the average is. That's the same, right? So that average rate of change doesn't really, okay, is not any different than it has been for anything else that we had, which is just the change in your y and then the change in your x between those two particular points, which really is just the slope of the secant. The instantaneous rates of change, right? Okay, so if we want to really find out, what is the instantaneous rate of change, okay, for that maximum right there, okay, well, we know when that happens, right? So it happens at pi, for instance. So we can calculate the instantaneous rates of change, okay, the same way. So that was f, right, of x plus our little h minus the f of x, and then divided by, and this was divided by h, and that was our instantaneous rate of change at x. Now for us, okay, so this x, we used to kind of say, well, this is at a, right, at some point a. So if you wanted to find out what this is, and if this is your a, right, if a is equal to pi, you can certainly plug it in and find out what that would be. So if we wanted to find the instantaneous rate of change. Now, if you wanted to find out what the instantaneous rate of change is on the positive side, which would have happened at a is equal to 2 pi, okay, you can find that as well. But I can tell you that, for these sine functions, because they're periodic, okay, they're also kind of symmetric around each other. So what you have is, okay, although at a is equal to pi, it might be negative, but the absolute value is going to be the positive value at 2 pi. So we can find what that is. I'm going to do it in fast-forward fashion for us, okay, and then we'll find what the instantaneous rate of change is at pi and at 2 pi, which is going to be the maximum rates of change for this sine function. All right, so let me do that in fast-forward fashion. All right, so welcome back. So here's pi. So basically, I just plugged it in. I pulled up Desmos just so that you can see. So within Desmos, I put sine exactly of this. So pi plus h minus sine of pi, okay, over h. And then, we can make h as small as possible. So notice I put it 0.1, and then the value is negative 0.11, and so on. So within here, if I keep putting, h smaller and smaller, okay, so notice what it is, okay, so it just gets closer and closer to -1, okay, so we're basically saying that, sine, or the instantaneous rate of change at pi, okay, for sine of x is equal to -1. Okay, and that would have been the maximum. And now if I've done the same thing, you know, and you can check, of course, you know, we can check from the negative side as well. Okay, and notice that within here, if we do that, it's going to get closer and closer. And notice it's actually spitting out -1 for us there. Okay, so here it gets closer and closer. I mean, eventually it just starts to round it off. Okay, so, you know, it's going to be -1 and then just alternating there. Okay, so as we get further and further and further. So we have that right there. Now, if I change this and I wanted to see what happens at 2 pi, and notice because of the symmetry, now it's going to be on the positive side. Okay, so we would expect that it would be basically 1, right? So if I put this in here, and then this would have been 2 pi, okay? And now I start changing this up, it should be just 1. All right, and notice it gets closer and closer, so basically 1. All right. So that's how you can find the instantaneous rates of change, no different than before. All right. Okay. So if I continue on here, I'm going to get rid of decimals, and I want to just give you a few examples. So here's one example, right? Okay, with working with these. So let's imagine we wanted to find the average rate on the intervals, so the intervals between 0 and pi/4. And if we want to find the average rate, well, this is no different, right? And what we've done is, okay, so we know our points. So we want to be able to find point 1 and point 2 with respect to these. And then we're going to just find the average rate by simply taking, you know, delta y over delta x, okay, between the points. So this would have been, you know, y2 minus y1 all over, and this would have been x2 minus x1 to try to find this. Now, if you're doing it in school, you most likely, or I don't know, I mean, I guess it depends. You know, if your teachers allow you to use your tools, then great. But if not, then you would have to, you know, substitute, right? So we would have to take x is equal to, so let's say this was x1, okay, this is going to be x2. We plug it in, we find our, you know, corresponding y2 and y1, so we find those points, and then we can do the subtraction and we'll find the slope, right? And that would have been our average rate. Okay, so, you know, here I'm going to pull up decimals because I'm just going to do this. I'm going to plot this. I'm going to figure out what the actual points are. So let's do that. I'm going to kind of close this off in here, okay, in terms of that. So let's see, you know, so this is f of x is equal to, so -3, let's say sine. So we're going to be, I'll plot this up. Okay, so here it is. You know, here's my plot. Now we can certainly plot this because we know how to do transformations, right? We can find the periods, we can find everything else. Now, if you've forgotten about transformations for sines, cosines, and so on, put up a link up above there for you. All right. And now if I wanted to find those points, okay, and then plot them up. So this is between 0 and pi/4. Okay, so let's, you know, kind of stretch this out in here. Okay, and let's put it in. So we want to plot the point of, so 0, okay, f at 0. All right, so we can plot that. We can label it. So that's our first point. And then we can plot, let's see, our second point. Okay, we'll label that. Let's say this was pi/4 and f at pi/4. All right. So that's that. We can label this. So those are the 2 points, okay, that I have there. So notice, so what is this going to be? It's going to have a negative slope, right? If we find the secant there, you know, so we can certainly join those 2 points up, and now let's see what we will get. Okay, what value that would be. So this would have been, so from those 2 points, you know, so we have, okay, I can write it in here. So y2 is -2, okay, minus negative, this would be 1 all over, And then this is pi over 4 minus 0. So notice this is negative 3 all over pi over 4, which really is negative 12 over pi, right? So that would have been our particular slope that we would have had. That's the average rate between those points. Now, if we want to find the equation of that line, right, of that particular line, well, you know, it actually goes through 0, 1. So we have the y-intercept, we have the slope, you know, so we can certainly do it. So y, I'm going to plot it in here for you. So y is equal to, so negative 12 over pi x, and then this is plus 1, right? So notice, there you go. It goes through those 2 points. Okay, we can see that happening. So that's one example. So the average rate, no different really than what you've always had. Now, here's another example. Find the instantaneous rate of change at pi. All right, so we can, you know, we can basically do the same thing as we did before. So, you know, the instantaneous rate of change. So if let me click this here. So if I do this, so to find it, now this is supposed to be at pi. So it's going to be pi plus that minus g at pi all over, right, h, and then this h is supposed to go to 0, and you can do it from both positive and negative directions, so we can see exactly what this might be. So, you know, again, I'll put it up in decimals. You can substitute the values into your calculators to see, but I'll try to put this in. So g of x is equal to, so negative cos x over 4 minus the 2. All right, so that's my g of x. Now trying to find what this is. So g, this is going to be pi plus h minus g pi. Okay, I'll put all of that in brackets there, divided by h. All right, I'll put a slider. And then let's, you know, make this small, okay? And now we can just keep chugging along and making it smaller and smaller and smaller to see what it is. So it's 0.17677 and so on. So it's probably, you know, there's pi involved in there somewhere. Yeah, but as we make this smaller, so it starts rounding it off. So, you know, this approaches, I guess, you know, if I put it in 1.7, whatever, 6. I don't know, I'm going to round it here to 4 decimal places. So approximately that. That would have been your instantaneous rate of change at that. Now, we can find it more accurately, okay, if we wanted to, but I think this is accurate enough, okay? So instantaneous rates of change, again, for these trigonometric functions, no different. And you could do the same, for instance, if you have secants or cosecants. The only thing is, please remember that, you know, for secants, cosecants, because they're reciprocals, you know, so they won't be defined at all the points. You know, if you've forgotten about those reciprocals, how to graph them and so on, I'll put up a link up above there. But finding the instantaneous rates of change and averages is the same, right? It's the same process. Here's a cool example. It's the last example here, because when you're studying advanced functions, and typically what happens is in grade 12, at least in the kind of Ontario or Canadian system, you know, you study those before you do calculus. And in calculus is all, especially in the beginning, interested in finding the derivatives, right, of functions. Now, what is a derivative? The derivative is basically the instantaneous rate of change, all right? So we just, you know, derivative is a little bit nicer to speak of, but from the viewpoint of advanced functions, you can think of it as the derivative, as the instantaneous rates of change, except the derivative tells you what it can be at all the points, right? So at all, instead of doing this every single time, you want to find it at a particular point, you actually find a function, right, which is the derivative, and it gives you, for any x, what the instantaneous rates of change is. You can just plug it in. Now, for trigonometric functions, and in particular, so here's something of interest. If you take sine of x, and let's say we wanted to find the instantaneous rate of change, right? And notice here it says at negative pi, at negative pi over 2, at 0, at pi over 2, at pi. And then it says graph it, right? So we want to find all these instantaneous rates of change. I'm going to do it on decimals, so it's a little bit quicker, okay, for us. But let's take a look. So I'm going to, actually, let's remove this. Let's clean it up right here on decimals. So what we have is, so it says h of x equals to sine, okay, of x, all right? So this is what we have. Just so that we can see this nice sine function. All right, so here we go. And now it's asking us to find the instantaneous rate of change, right? And then graph it at those points. So we're going to be finding the instantaneous rates of change at those points. Okay, and I'm going to graph those points along. So at negative pi, I'm going to graph what that is, the instantaneous rate of change, and so on. Okay, so this is what I'm trying to find. I'm trying to find points. Okay, I'm going to try to find the point negative pi, and then I don't know what the instantaneous rate of change is there. So that's going to be my y value. Then I'm going to find negative pi over 2, and I'm going to find the instantaneous rate of change. So you can create like a table for yourself of these points. Then it's 0, okay, and then find what that is, and so on. Okay, so let's plot these up, okay, within here and try to see what they will be. So the instantaneous rate of change at negative pi is going to be, okay, so this is going to be my first point. All right, so I'm going to say h right here. H, you know, so this is at negative pi. Negative pi. Actually, you know what? Because I'm going to be filling it, I'm going to call this a. Okay, and I'm going to replace the a. So plus the h, right? Plus the h minus h. Oh, I call this h and h. That's okay. Okay, so this is going to be a. So that whole thing. Okay, let me. Well, that's not what I wanted. So here it is again. So h. Let's not call it h because I'm using h for the. So let's call it g. Okay, g of x is equal to sine of x. All right, so that's what we have. And now what we want is we want g, okay, a. I'm going to be changing a there. G, a. It's h minus g at a. Close this all over h. Okay, and I want these. So first we want a at negative pi. All right. So this we're going to make very small. All right. Okay, so notice the answer is negative 1. Okay, so within here, so this is negative 1. So that's my instantaneous rate of change. And I can now plot this point. Okay, so I'm going to be plotting. So this is negative pi, negative 1. All right, label. So that's my first point. And now, okay, I'm going to do the same thing, except I'm going to have a, that's going to be over 2. So notice 0.0, so this is 0, okay? So this is 0. Now I'm going to plot it, okay, I'm going to find the instantaneous rate of change at 0. And I'm back, and now I'm at 1. All right, so now I'm at 1. So I'm going to start plotting these out. So I have negative pi over 2, 0. So that's my second point. Then I had 0, 1, right? Okay, so notice, okay, so this is what I have here. Okay, I have these points thus far. Now I wanted to find, so pi over 2. All right, so this is going to be pi over 2 is next. Pi over 2, the instantaneous. So that's back to 0. So pi over 2. Back to 0. Okay, and then at pi, which is going to be negative 1. But I just want to show you. Okay, so that's that, and notice it's negative 1. So at pi, it's negative 1. So now we have these points, right? And this is going to be pretty cool that you're going to see something like right here. And now we could continue, right? And we can continue these and finding what the instantaneous rate of change. Now what I want to show you is, because do we notice, can we deduce something? Check this out. So now I plotted cos of x. And notice it went through all of those points. Pretty neat, right? So it turns out that the instantaneous rate of change at any point of sine of x is actually cos of x at that point. So if we wanted to find out, and this goes, so if we wanted to find out this, so if we want to find out the instantaneous rate of change, okay, of sine of x at negative pi, then that is equal to cos of negative pi, which indeed is negative 1, right? So if we wanted to find out this, instead of doing these calculations over and over, like doing this silly stuff here, you can actually find what the instantaneous rate of change is at any point of sine of x, and it's cos of x. And that is called the derivative of sine of x when you finally get to calculus. Okay? And you can now try, if you would map cos of x and try to find the instantaneous rates of that, you would actually notice, and you started plotting these things out, and you wanted to deduce what the instantaneous rate of change is at any point, you would notice that it would be negative sine of x for cos of x. All right? So I'll leave it at that, okay, for this video. I think, finding average rates and instantaneous rates of change, you probably had enough at this point. So you can certainly try to figure them out. You remember the calculations. And here I presented a few examples for you. All right. Thanks for watching. Okay. Happy studying. Good luck in your advanced functions courses and in grade 12. Okay. Bye, everybody.